Welcome, everyone, to the first meeting of the Memphis Astronomical Society for 2026 calendar year. Happy New Year to all. I can tell that some of you had a Merry Christmas and got telescopes or telescope equipment, as proved by the number of cloudy nights we've had lately. In fact, we get a clear night when? On a full moon, right? That's the cloud gods saying, you've been buying too many telescopes. But I hope you all get a chance to get out and enjoy your telescopes and new gear soon. The Memphis Astronomical Society meets once a month at the first Monday of the month typically, and we have our general meeting and a presentation in a related science and hopefully astronomy in most cases. We have a QR code that proves we're real. Scan that QR code and that'll take you to a web page where you can join the Memphis Astronomical Society or sign up for our newsletter. Not our newsletter, but for our email notices. Join the Memphis Astronomical Society is $25 a year, a good deal at twice the price. So this is the web page that it takes you to if you scan that QR code. On our website, we have a calendar. You'll notice this month we don't have a lot of observing sessions scheduled, but we have one on the 10th, and I'm thinking we need telescopes, and I'll be making a presentation at Pinecrest, followed by observing. We have a few new members this month: Amanda LeCain, Shannon Fagan, Ward Archer. I'm not going to embarrass myself or Mr. Madden by trying to pronounce that name. So welcome to the Memphis Astronomical Society. I'm sorry I don't have that vocabulary. Alan Elliott and Alina Petrova, welcome to the Memphis Astronomical Society. We have an excellent newsletter, and if you aren't a member, you don't get it. But if you are a member, you should get it and take a look at it. This month, we've got a couple of new features that Steve has added. We've got a list of things to look at in the night sky, things to go out and look at. A lot of these are binocular objects. Then a new batch of photographs from our many astrophotographers. And then the second new feature for this month, and I love this. And when I first looked at it, I said, why has he got two star charts in here for this month? You know, he must have slipped up and made a mistake. But alas, he did not. This star chart shows you the area of the sky that you're probably not going to see from the city where the light pollution is so bad. So this will show you what you probably can see, mostly overhead from the city, but this is the light pollution filtered sky chart. So thank you, Steve. Excellent idea. Great innovation. And then, of course, we have our calendar attached to the newsletter as well. So almost in and of itself worth the $25 annual fee. We have an astrophotography group that typically meets once a month. This month, on Wednesday, January 21st at 7 p.m., we'll have a meeting of that group on Zoom, and you can check out the topics: presentation on dual band filters, some discussion topics, and then some future topic: processing images taken with robotic telescopes. That will be fun as well. So join the Memphis Astronomical Society and get involved with our astrophotography group. This is for people with iPhones and eyepiece shooting, and up to and including way more elaborate setups than that. But beginner to advanced. We have a vendor that provides swag for us and sells their stuff with our logos on it. And if you'd like to show the public your dedication and interest in the Memphis Astronomical Society, check them out. They've got a lot of cool stuff there. I'm a huge fan of their mugs. All right, tonight's program. So Dr. Robert Nemiroff is going to tell us about what at least appears to be faster than light. Typically, these are jets that are of particles that are streaming away from black holes, and I suspect that's what we're going to be looking at, and or other things. And but there has been controversy and question about how it could do that at speeds faster than the speed of light. I think those rumors will be debunked. So anyway, I could be mistaken. Maybe they are. I might learn something new tonight. So Dr. Nemiroff, we're ready for you if you are.
Okay, thank you very much. It's an honor to be. Well, I'm going to still share my slides deck here, so you may get a brief shock. Okay, now slideshow, play from start. There we are.
There you go.
If you're not seeing the first slide, and I'm just speaking out stuff you don't know, please tell me, please. Anyway, here we go. Faster than light, how distant galaxies can do it without disappearing. You might have heard that distant galaxies are going away from us faster than light. So we'll get into a little bit how that can be perfectly compatible with Einstein's general theory of relativity and special theory of relativity. So there will be like no equations tonight, but there'll be a lot of concepts, a lot of cool concepts. So there'll be other relativistic oddities described. Can you see my cursor move around here? Someone moving it around? Oh, okay, good. So I can use that to point. Okay, so I am Robert Nemiroff, and I'm professor of physics at Michigan Technological University, which is way north of here. It's in the Upper Peninsula of Michigan. And so some of you might recognize this is today's date. So let's go one more slide. Ooh, here we go. Who is this guy? Well, we're going to get to what you probably, oops, so I got my PhD in the late 1980s, predicting something, among other people, predicted something called gravitational microlensing, which is that stars can magnify light behind it through its gravitational effect. It's been seen many times, but back in the 80s was just in theory. And so we tried to think about how useful it would be. So in the 1990s, I moved on to something called gamma ray bursts, which are huge flashes. They're supernovae that are visible in the gamma rays, and they're visible far across the universe. And so I argued in the 1990s, along with many other people, that these things are far across the universe. But many people back then thought they were relatively close by, some even in the solar system, some just in our galaxy. But it turns out that the vast majority of them are far across the universe. And you can constrain, part of my research constrains attributes of the universe with these gamma ray bursts. What I'm best known for is in 1995, a colleague and office mate of mine and I founded the Astronomy Picture of the Day from NASA, and you can get it at apod.nasa.gov. So we've been going for 30 years on that. And So real proud of that. I understand there's a lot of good astrophotographers here, so I'm happy to take questions on that, even though that's not the topic of today's talk. Um, so another thing I've done in 1999, along with a different colleague, I founded the Astrophysics Source Code Library. So a lot of science and physics and astrophysics is done with computer codes. But in the 1990s, there wasn't a tradition of sharing your code. You'd share your paper, you'd share your graphs and your equations, but the code is something that would remain behind the scenes. And some people and I thought that was really not a good idea because you could make mistakes in the code. Other people could then take your code and write better code, just like they can take your equations and write better equations. So we started a library, a registry of places where people can store and make available their source codes. And so now, finally, many years later, we have 3,400 codes plus that are linked there. And so we're real proud of that. And now journals and even funding agencies are saying, yeah, you know what? You should really share your code because otherwise, if there's a mistake in the code, no one's going to know. And there's going to be a lot of mistakes and a lot more mistakes in the field, and the field won't do so well. It's much better if everybody, if there's more transparency. So now we're becoming more popular like that. In the 2000s, like every decade, I have another strange idea. 2000s, I was led in the development of all sky monitors. So these were fisheye lenses that you can see the entire sky. You don't point these things, they see the entire sky. So we developed these. The CCDs they had back then were pretty small, and so we tried really hard to get a fisheye lens to focus the whole sky on a small CCD, and eventually we were successful. And then we started deploying them all over the place. But then they became so inexpensive and they were so useful to major observatories where we were deploying these. Major observatories said, you know what? We get the idea. We're going to do it ourselves. So now most major observatories have what we would call a continuous camera. And they're still good for monitoring clouds, and even the brightest stars like our sun are variable in some level. In 2010s, I mostly helped raise a teenager. So that takes some time. Now, in the 2020s, though, where we are now, some of you might notice, I've been studying something called relativistic illumination fronts. So these things were surprising to me, and they deal with the speed of light, but they don't allow information to travel faster than the speed of light. But you can still get some really cool effects. Effects that Einstein was pretty much aware of some of these. The others he wouldn't have been surprised by, he just didn't go down that path. So it's not really controversial, but it is, in my opinion, really cool. And so I've published a bunch of papers on these, and I'm real happy to speak to the Memphis Astronomical Society about these because I just think about these, and I have students that think about these a lot of the time. Okay, so past that, I wrote a book, and it's in fact this book. I have to keep it in front of me or else it'll black out. Look, it's a spirit. So it's called Fast and Light, and it's available on Amazon. But as you'll see from the end of the lecture, if you send me an email saying that you've attended this lecture, I'll send you a digital copy free. So that might be cool. So here's some people who've reviewed it. Okay, so let's get started on this faster than light stuff. And so please take a moment to ponder these questions. Now, you may be asked to consider, you will be asked to consider if any of these things can move faster than light or not. So a lot of these questions are pretty binary in a sense. It's like, can it go faster than light or can it not? So if you think that nothing can, just say no, 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 no. But you might be surprised by some of these. So let's get started. Thanks. I see in the chat that people are giving the URLs to Astronomy Picture today and the Astrophysics Source Code Library. Thank you for doing that, Rick. Okay, so first of all, can you move faster than light? And so there's three main answers to this. One is yes, one is no, and the other is in the middle, maybe so. So in the book, I frequently have Shruggy, who considers some of these questions. Some of these questions are in the book, some of them are not. So Shruggy doesn't really know. Just like many times, and I've been fascinated with this for much of my life, as well as astronomy and astrophotography. This has been another facet. So I've shrugged to myself inside many times, and sometimes been very happy to learn the answers. So if you want, you can chat the answer, but many people I understand they might be getting it wrong, they don't want to say, or something like that. So you can just think it to yourself, or maybe write it on a piece of paper, so you might remember what it was. So the answer to this one is no. I think most people are getting this. So according to Einstein's special relativity, 1905 is when he published it, you yourself cannot accelerate past the speed of light, c. So what happens is if you try relative to an observer that's not moving, so the way I usually, well, is that your mass and moving energy increases, and it goes infinite. And so you don't have the amount of energy needed to accelerate past the speed of light. Some people think that there's things that have mass that go faster than the speed of light. I'm not in that group. They call them tachyons. So you probably won't, besides here, you won't hear much about tachyons because I'm oddly enough deep down a skeptic about many things. But anyway, so it's that advantageous not even to try it. You can't go faster than light, but there's more. Stay tuned for the next slide. Can shadows move faster than light? So here you think you can do everything first and your shadow follows you, but maybe your shadow can do something that you can't do. Maybe your shadow can move faster than light, whereas you can't. Is the answer yes, no, and I didn't have a maybe so. Okay, someone has read the title of the book, and people are generally getting it right. So we'll say yes, your shadow can move. So an example is, let's say you shine a flashlight at the moon. The moon's not going to care. There's no astronauts on the moon now. There's a few robotic explorers that are sitting there mostly. But let's say you take your shadow, your flashlight, or your laser pointer, and you point it at the moon. Then you take your hand, you're pointing at the moon. You take your hand and you move it in front of that. So you're going to create a shadow of the flashlight on the moon. So when you move your hand across the flashlight beam, you're going to create a shadow that appears on the moon. Now you can't see it because it's too dim to see, but it's easy to show. And there's other examples that don't require them. When I'm using the moon, because everybody, especially in the Memphis Astronomical Society, has heard of the moon and seen the moon. The moon is just a good example. So your shadow then, the shadow, the places where your fingers go across, you'll see dark spots move across the moon, and there's no limit on that speed. You can have something even further out, and again, see that the shadow itself can move faster than light. This is not controversial. There are actually famous textbooks that you can find this in. Okay, so here we go. Can shadows transfer information faster than light? So let's say here we are on Earth, and we can send, signals to the moon. It'll take what? I don't know, a second or so, about a second. So, but maybe we can use special shadow technology and communicate faster to the moon than it would take light to get to the moon. So the answer to this is either yes or no. Okay. I could whistle the Jeopardy theme, but that gets old after the first time. Okay, and the answer is no. You cannot transfer locally created information faster than light using shadows. And we're going to get more into the details of this later. So just because shadows can do it doesn't mean this is a new mode of communication that's without limit. But let's go on. That will be a teaser for the future. Can laser spots move faster than light? So let's say I have a laser, and these are actually my fingers. I know it's not a laser. If I was a superhero, it might be a laser. So anyway, I move this around, and therefore I shine my laser pointer in different directions. That makes a spot on a wall, on a cloud, on the moon. Can that spot move faster than light? And let's see. Okay. Steve is actually typing in the question. Ooh, we have some division here. That's good. So if you would ask me this, 30 years ago, I would give you a different answer than I will give you soon. And so now, drum roll, please. The answer is yes. Sorry, the text is a little bit small. But so here's an example. Let's say, hypothetically, obviously, there's this big dome out there that's 1 light year away. Maybe that's where all the stars are on, and we're just confused because we think there's stars far away. I don't really think that. But let's say there's this big dome, hemispherical dome. Now you take your laser pointer and you point it at one half of the dome, and then in 1 second you go all the way to the other side of the dome. So what's going to happen is it's going to take a year, because it's a light year away, for the photons to go out of your laser pointer and hit the edge of the dome. But then after that, it will mimic what you did, and in 1 second, that spot will move all the way around to the other, in 1 second, all the way to the other end of the dome. But since it's a 1 light year radius there, that spot is moving faster than light. However, that's so that spot moves faster than light. However, again, we get into the same paradox as before. Does that mean, well, I don't want to give away future questions. So let's just pause there for a second and go to the next question. Okay, all right, so this speed could be considered, and this is a phrase that I've worked hard on, the orchestrated superposition of unrelated photons. So the photons that hit here, when the laser pointer is pointing like that, and the photons that hit here, those are different photons. So there's no photon going around, so that photon itself, so the photon only comes out from the laser. So these are just supposedly, these are unrelated photons that are just hitting in different positions. So there's another thing called the holiday lights or Christmas lights illusion. So let's say you have two lights. So this, I've noticed this when just bored and staring at Christmas lights. They blink on trees or on wreaths or something. So you look at them and sometimes one blinks, sometimes the other blinks, and you can sort of think of the blink going from one to the other. But there's nothing to stop them from blinking at just about the same time. And if so, then you can sort of think that the sooner this blinks after this, the faster the blink jumped. But there's nothing really going between the two. These are two unrelated events. So it's, again, the orchestrated superposition of unrelated flashes in that case. So you can have orchestrated superpositions that appear to have something go faster than light, but that something isn't a photon. It isn't anything with mass. Still, it appears to your eye. You're looking at it. Ooh, I looked at those Christmas lights. They look to flash real fast. The same with the laser spot on the supposed dome that's 1 light year away. You can say, wow, that laser spot's moving quickly, real quickly, faster than light quickly. So the question is now, and probably everybody will get this right at this point, can laser spots transfer information faster than light? So we have all these civilizations we've made contact with. I guess you haven't been reading the news, out at 1 light year, although Alpha Centauri is about at 4 light years. No, it's about 1 light. So then we want to communicate with them, but we don't want to wait all the time it takes for light to get there. We want to communicate faster. Can we use these laser spots to communicate faster than light? So people are getting it right. So the answer is no, because the photons move out from the laser. And then when they move out from the laser, they only move out at the speed of light. So nothing here is moving faster than light. The only things that appear to move faster than light is the spot, like the shadow. The spot and shadow appears to move faster than light, but it is not something that has mass. It is not something that has momentum. It is just the orchestrated superposition of unrelated events, but it appears to move faster than light. So when you see a laser spot move on the wall, you think, oh, I can give a speed to that. Okay, sure. You can give a speed to many things. That speed doesn't carry any momentum, though. So you're not going to knock anything over with that. You can only knock things over with the photons that go out from it and give momentum in that direction. So on the dome, the people who live over here will see your information that the laser light is on, and 1 second later, well, 1 light year away, they'll see your laser go on, and 1 light year in 1 second, they'll see your laser go on. So it's 1 second later, but there was no communication from all the way over here to all the way over here. All the communication came from the laser itself, and the laser itself shoots photons that only go at the speed of light. So, okay. Can muons move through water faster than light? So the first question is, muon, what's a muon? So I could use protons. A muon is an elementary particle that happens to go through water relatively easily. Protons, they don't go through water very well. Everyone's heard of protons, many more than muons, but protons, they get stopped because they hit stuff. But muons don't care for a much longer, for several meters. So they can move through water. But the question is how fast? Can muons move through water faster than light can through water? So I'll give you a second or two. So the odd answer to this question is yes. So the muon can move faster through water than light can through water, but it can't move faster through water than light can through vacuum. The fastest that anything with mass or momentum can go, so far as we know, locally, is the speed of light in vacuum. But light, when it goes into water, slows down by about 25%. So suddenly, when you have light moving through water, the phase and group velocity, if you're a physicist, that would make some sense, but just think of it as speed. The speed of light through water suddenly dropped real quickly to 25% of what it used to be. But a muon doesn't do that. A muon slows down, but it slows down much more slowly. So if you had the Olympics down a swimming pool, I guess across a swimming pool, and the participants in this Olympics race were a photon, an optical photon, and a muon, and you both release them at the same time, which one hits the far side first? And the answer is the muon does. Because the muon stays close to the speed of light in vacuum, assuming it started at that, but the photon quickly drops by a quarter. A muon is kind of a heavy electron, yes, but it's not, it has some different properties. But it's similar to a heavy electron, it's true. Okay, so now we come back to something that's in the title of the talk. Can distant galaxies move faster than light? So this is a little bit, we're entering a little bit of a different thing here, a different paradigm here. Yes, no, and there's always a maybe so. So if you just want to say C, maybe so. Okay, I'll give people a little bit to think about this, or you can just enjoy the show. You can guess, you can write down your own answer, you can tell your cat or dog, or, all right, so here we go. The answer is yes. So there are galaxies in the universe that you can see that are actually now speeding away FTL. So FTL is fancy terms for faster than light. Instead of spelling it out all the time, sometimes I'll abbreviate it FTL. So why is that? See if I have that in the next question. No, let's go back. So why is that? Why can galaxies do that? Because, well, according to special relativity, the speed of light is a local speed limit. Nothing with mass can pass you. I'll just start saying nothing again, excluding laser spots and shadows and things. Nothing with mass can pass you going faster than light. But in general relativity, things far away aren't passing you. And so general relativity allows higher speeds far away. So in fact, as you go farther out in the universe, things are going faster and faster. And so the faster they go, it turns out they can even go, compared to you, faster than light. And this is a solution. in many different solutions to general relativity, sometimes called the Friedmann-Robertson-Walker metric is some of the most famous solutions, but this is well known and not controversial. Einstein knew about this. Okay, so here's another one. Can scissors, I should have brought scissors cuts. Can scissors close faster than light? So this is a little bit trickier. Yes, no, we've got some division. Yes, you can attribute the expansion of space to be the thing that goes faster than light, but that's actually, you get into a bit of semantics. It's the mathematics of general relativity that describes what goes on. But many popular accounts describe it as the expansion of space. That's true. So you can be shruggy here, shrug away. Okay, so the answer to scissors is most scissors, no, but some scissors, yes. So actually, a student and I published a paper on this because we saw on the internet that sometimes this was debated in physics forums, and sometimes they would get the answer a little bit right, and sometimes a little bit wrong, but there was no comprehensive discussion of this. So we decided to publish papers on this. And one of the kinds of papers I publish are primarily education papers in journals like the American Journal of Physics. The American Journal of Physics is a journal that has mostly educational papers and is actually statistically harder to publish in terms of number of percentage of rejections than most physics journals, other research journals. I do publish in research journals as well. So the scissors that can't close faster than light are typically the ones that go where you take both things moving together. Then the vertex, which is in the middle, I don't have a third hand, but picture the vertex between the two, that moves up in this case. In that case, you can't make the vertex move faster than light because when you move one scissor, then the information that the scissor handle, the scissor blade is moving can only go up the scissor at the speed of light, speed of sound actually, but it's slower than the speed of light. So the end of the scissors doesn't know that this part of the scissors is already turning. Therefore, after some arguments, it turns out that the vertex can't go faster than the speed of light, but there is a scissors we found that does, and that's a guillotine scissors. So if you have this and a guillotine comes down, and the guillotine is a solid blade and it comes down, and the vertex angle is just this small thing right there, that if this angle is close enough, then what happens is, if it was perfectly parallel, you'd have the whole thing close up at once. But then if you just tilt it a little bit, you can get the vertex to move across arbitrarily fast, depending on how slight that angle is. So a guillotine scissors can have its vertex move faster than light, strangely enough. So let's go back to the scissors again. So with the scissors, what would happen if you put a little marble in there? Can this be like a marble gun and maybe shoot the marble faster than light? And the answer is no, you can never accelerate that marble to go faster than light. That can't work. It would take an infinite amount of energy. Most scissors have nowhere near an infinite amount of energy, so something would have to break along the way. But it is a really interesting topic to consider and was surprising. Okay, so this is kind of cool, kind of interesting. So when you turn on a room light, can the dividing line between dark and light on the walls, can that move faster than light, FTL? So let me make this more vivid. So there's a standard sized room, and there's one light bulb in the middle of the room, and the light bulb is out. So you peek your head in the room, and you say, oh, it's dark in there. So then you turn on the light, tink, tink, and the light bulb near the middle of the room, it goes on. Surely a few seconds later, the entire room is lit up by the light bulb. That's not so. So at some point between when the light was off and assuming the light turns on instantaneously and the light was on, the entire room becomes illuminated by the light bulb. So that means that on the walls, there had to be a starting point where there was some light on one of the walls, and then that light expanded and eventually incorporated the whole room. So if you could see fast enough, you could see that. But you can always take, if during that small amount of time, and it's nanoseconds actually, you can draw a circle around where the dark is, the light is that's moving to the light circle that's expanding to completely illuminate the room, and you can see that, wow, that light circle is moving out. And so the question is sort of how fast can that light move out? Is it constrained? It's move faster light, or is it not? So once again, the answer, strangely enough, a surprise to me and many other people, and we published a paper on this too, because it's actually a simple way to prove this. The answer is yes. The dividing line between light and dark can actually move faster than light. If you could see fast enough, and when you turn on room lights, assuming, even though it's shades of light, you could actually see this. If you could see, if your eye integrates every about 10th of a second. So you're seeing a movie in your life where the frames update every 10th of a second or so. But if you could reduce that by a factor of 10 to the 9 down to the nanosecond range, you could see the illumination fronts go, and you could time it, assuming you had a stopwatch fast enough and your brain could run fast enough. You could time it, and you could say, wow, those illumination fronts are really flying. The simple way to prove this is, so light bulb is here, and it illuminates the closest point to it first. And then it illuminates another point up here. So these are just two canonical points on the wall. So here's the wall, here's the light. Turn on the light bulb, it illuminates this first. And then later on, it's going to illuminate here. So what happens is light moves the speed of light here. But light also goes the speed of light to here. But this distance is shorter than this plus this. But we know that this one is at the speed of light. Therefore, for those two to be at the same time, for it to be lit up at both times, this leg has to be faster than light. And that's actually a general argument. So it's pretty cool. I thought it was really cool. That's the kind of things that I think I'm kind of geeky think is cool. Besides astronomy pictures, which I thought have been cool also for really long. Okay, so now here's another one. When you turn on a room light, must the dividing line between dark and light on the walls, must it move faster than light? We've established that it can move. Does it have to move? Shruggy's thinking about it. So, I'll give you a clue. This one was a surprise to me, but it's the same proof, and the answer is yes, for the same reasons. So here and here, you can't find another location. Even if you tilt it this way or that way, you can't find another orientation where that doesn't work. So every orientation, it turns out, when you move out at speed c and then you have the illumination front connected, every orientation that works with. It doesn't matter the tilt of the wall. And once it doesn't matter the tilt of the wall, then it must be always true. Surprising to me. And it was in our paper. And this one was in the European Journal of Physics. There's another educational journal. So you can come up with superlatives. They're fun to say. Impress your friends and family. All illumination fronts across all objects are always superluminal. And the reason why we didn't really, well, we could always prove it, but we can't see that fast, or it would have been totally obvious to us. We can't see that fast. But now, with new technology, with like really fast videos that you can sometimes find on YouTube, you can actually see it. And there are YouTubes on videos that show things like this. Okay, so am I having fun here? Yeah, I'm having fun here. Are you having fun here? Yeah, maybe a little bit, maybe more. Some of you seems like you're having more. Is there anything practical going to come out of this? Is anything involving superluminal motion practically useful? Yes, no. That's a little dry tonight. I'm going to keep sipping water. C. I like it. Okay. Ooh, there's Struggy in a ASCII code. Okay, so the answer to this one is yes. Actually, it is. So what happens is you can gain by watching superluminal fronts move on walls and objects. You can get three-dimensional information. So almost all photography, as you might know, astrophotography as well, is two-dimensional information. You see a nebula, you see family members, friends in a 2D photograph, and you really don't know how far out they are because you really have just one lens. Now you have two eyes, and so you can use parallax of that. But with photographs, most 2D photographs, you don't know. But if you could see the illumination front move across it, you could then say, oh, I can see how fast the illumination front is moving. I can tell you how much depth there is there, and it gives you 3D information. So for instance, let's say you have an aircraft with a flat wing, so moving toward you or moving in some direction. If you sweep that wing of that aircraft at just the right speed, you can have the light all come back to you at the same time, and you see a relatively bright flash. And that tells you that the superluminal speed was very high on that wing, and that tells you the only angle that could happen is some angle, and you can say, oh, you know what? I know what kind of jet that was. This is a cousin to something. This is cousin of LiDAR. LiDAR with many phones do LiDAR. So that bounces things off and times how long it takes for things to go back and forth. But if you could actually make movies of things, it gives you very similar information to LiDAR, but it gives you relatively continuous. But LiDAR is easier to encode, so it's easier for your phone. But this can be useful because 3D information, knowing 3D information is useful. It's actually knowing how illumination fronts move in astronomy can also give you 3D information as to the nebula. You can say, oh, I can see how fast that illumination front is moving across that nebula. Assuming it's a tame geometry and not all crazy, you can say, you know what, I know something about that nebula now that I didn't know before. I know, how deep it is, how long it's taking for different things to happen there. And so that's true of Hubble's variable nebula at some level and some other nebulas, but it's relatively unexplored. And so we're actually hoping that the Rubin telescope, the Vera Rubin telescope, which gives a lot of high temporal resolution data, might allow us to see more 3D information about different nebula and things like that. So that was a surprise to me. Okay, so laser spots. Let's go back to laser spots. Okay, so this is sort of what got me into this game. I couldn't figure this one out, or it's driving me crazy. So let's say you take your laser pointer and you have an infinite wall. Okay, there's an infinite wall, the wall nearest you. We don't have to know which one it is. So you take a laser pointer and you sweep it across an infinite wall. At first, the laser is not pointed at the wall, so there's no spot on the wall at all, no spot. Now you sweep it across the wall, and then it starts pointing at the wall, and then you go all the way across, and eventually you see it all go all the way down the wall. So here's the first question for this. Uh, where is the first spot appear on the wall? So originally the laser was not pointed at the wall. Soon it's pointed at the closest spot on the wall. The wall's not so far away, it's a meter away or something like that, but it's infinitely. So where does a laser spot first appear? So here's three answers. One is the nearest to the laser, right there. Oh, right here on the wall. The next is infinitely far down the wall because it was pointed away, and and the third possibility is, well, maybe not infinitely far down, maybe not the closest, maybe somewhere in between. There was the A, B, or C. And so people are weighing in. We got a lot of C's. Okay. So, drum roll, please. This drove me crazy. The answer is somewhere in between. So it's not nearest the laser because you know it was pointed slightly next to the laser. You know it's not the nearest point on the wall because you know the point next to the nearest point on the wall was illuminated before it was because it was here and then it was there. But what about infinitely far down the wall? Well, it takes light an infinite amount of time to go infinitely far down the wall. And you know that you could see the laser spot right near you relatively quickly, and that's not an infinite amount of time. Therefore, it's not the nearest spot. It's not infinitely far down the wall. It's somewhere in between. That's strange. Where is this in between spot? Okay, so back down the hatches. Here we go. Which direction, so it's the same thing, it's laser spot on the wall, down the wall. Which direction does that laser spot move? So again, you went down the wall. It's not the closest point. It's not the most infinitely far down the wall. It starts somewhere in between. But where does it go from somewhere in between? Does it go toward the closest spot on the wall, toward the laser? Does it go away from the laser down toward the furthest point, infinitely far down the wall? Or is it something completely different? This drove me crazy. And it's discussed in the book in some detail. Okay, so drum roll, please. The answer is something completely different, as Monty Python would say. What happens, and you can show this mathematically, and actually has been seen in the lab, is that two spots are created. So the midway, not midway, but somewhere down in the wall, one does move this way because you can see that one move by you, and the other one then moves down and eventually will be infinitely far down the wall. So so instead of just one spot moving, that spot breaks into two, and you get two spots, one moving toward you, one moving away. And this is an example of something called relativistic image doubling. So it was something that I and my group had rediscovered. It was occasionally mentioned in the press previously, but only in passing in a paragraph or so. But we really have to start study this because it's relatively unknown. And again, if we could see at the nanosecond scale, this would be like really common. We'd understand this. But it's not, but it happens. But on the scale of astronomy, when things are really big, it probably happens a lot more and a lot more slowly so that we can see it. So one of my major research topics now is this. When do you see relativistic image doubling? What can it tell you? What information is embedded in this image doubling? When you see it, you see two things move away. Oh, okay, now we know something. What does it tell you? It can tell you some things that you didn't know before. You look for it. You know to look for it. Okay, so let's go back to muons, which are like heavy electrons, and but they don't hit things in water so easily. So these get a little bit harder. So okay, so now we have a muon moving through water faster than light can through water, which I'll call FTL. And this liberates isotropic, incoherent. You don't have to understand why this is, but it's important for physics. Thermal radiation as it goes. So the muon comes directly toward you. What do you see first? So this muon's going through, it's liberating light, but the muon is moving faster than the light. So what do you see first? It's coming right toward, do you see the muon first? Do you see the thermal radiation, the muon liberated? Or do you see something completely different? So, some disagreements here. So we are A. So you see the muon first, because the light that the muon liberates, the muon's faster than that. So you're going to see the muon before the light it liberates, because it's moving faster than light can through the medium. So the muon wins. So what happens if it comes to your eyes? Boom, hit by a muon. And then you see, oh, zoop, you see the light the muon created later. Not controversial. The muon's faster than the light. You see it first. Okay, so a muon now, more conventionally, moves through water slower than light. And it also liberates thermal radiation as it goes. The muon again comes directly toward you. What do you see first? Do you see the muon? Do you see the thermal radiation the muon liberated, or do you see something completely different? Or you just don't, you're just whatever at this point. Maybe you can do D, whatever. Okay, people are getting this right. So it is, you see the thermal radiation first. So when the muon moves slower than light, you see the radiation it creates first because that light is moving faster than the muon. But when it was moving faster than light, you see the muon first. Okay, so now the muon enters water faster than light, but because everything slows down, especially in water, it then slows to slower than light, and it comes directly toward you. What do you see first? So now it's doing both. It first entered faster than light, and it slowed down, and then it was moving slower than light. What do you see first? Do you see the muon? Do you see the thermal radiation the muon liberated, or do you see something completely different? So it's getting kind of complicated at this point. So you can just go for the ride if you want, or you can take guesses. So the answer is basically C, which is kind of strange. So what you see is relativistic image doubling. The thermal radiation from the muon, just as it entered radial speed, dropped from faster than light to slower than light. So when it was moving faster than light, you see the muon first, but then you then see the light the muon created back off. But then when the muon was slower than light, you see the light from it first. So the first thing you see is nothing, and then you see both the faster than light and slower than light tracks at the same time. That's just like if you had the laser pointer on the wall, you would see the two things move away at the same time. Eventually, you're going to illuminate infinitely far down the wall. Eventually, you're going to illuminate the closest point. They're going to be, at similar times. You have to have two. You have to have relative image doubling to have two spots do that. So one moves away from you, one moves toward you. Um, so, um, so this is an example just with muons through water that relativistic image doubling occurs. And it's seen, but it's not, it's complicated to see exactly how it's seen. The point where you see it first, when the relativistic image doubling occurs, you're seeing a relatively long path of the muon all at the same time. So it's really bright. And so people gave that a name that's called the Cherenkov cone. And many people haven't appreciated that the Cherenkov cone, which we totally agree happens, is related to relativistic image doubling. So that's one of the things we're publishing papers on, and we're trying to show that all these things are related. Okay, you can also do this not only if the muon enters faster than light and slows, but if the muon just passes you by. Because really the most important thing is the speed radially toward you. So if it's far away from you and coming toward you faster than light, then that's one thing. But then as it passes you by, the speed toward you drops to slower than light. So what you do is you see the bright relativistic image doubling event right when the speed toward you drops from faster than light to slower than light. And then you see two things go off in different directions with a big flash, and then two fading things pulling you off in different directions. So that's the answer to that. So rather than quiz you, I'll give you the answer. C, you see it first location. You see it first at the location where its speed toward you dropped from superluminal to subluminal. From there, you see two images of the muon as it liberates incoherent isotropic radiation. One is moving forward along the track when its radial speed is subluminal, and at the same time, one is moving backward along the track when its radial speed was superluminal. And again, it's not this muon at no time moves faster than the speed of light in vacuum. This is done because the muon moves faster than the speed than light does through water, and that's well known. Cherenkov radiation is well known. Okay, so this is a visual demonstration of this. This isn't actually a quiz. So I'm going to run this twice. I'm going to talk through it the first time. This is done by a student of mine. So this is, here you are, you're the dot here, and here you're going to have the muon moving at twice the speed of light, which it can't happen actually. So every time it passes some point, it liberates a photon that comes to you. So you see the photon that comes from not the middle of the track, but from not either end of the track, either first. And then eventually you see others. I'm going to rerun this back again. So here comes the muon going past you at 2C. So here's the photons it liberated. So you're going to see the photon that came from here first. And then you're going to see photons coming from the other direction second. So there's the flash, and then you see two images moving off in different directions. It's actually simple geometry. Okay. So it appears brightest from you in the middle. I'm not going to get into this detail. I think I'm running a little bit long, so let's keep going. Let's do the last part, cosmology. So why do distant galaxies move away from us faster than light? Is it because the entire universe is expanding way faster than light? And the galaxies are caught up in the expansion? Is it because the universe had an inflationary epoch early on that caused superluminal motion, and it's still going on? Or is it because dark energy is causing the distant universe to accelerate in its expansion? This is again back to the title of the talk, back to general relativity as opposed to special relativity, where the solutions are a little more complicated, a little less cerebral, but really cool. Okay, so the answer here is A. The speed of light is only a local limit, as I said before, in special and general relativity. So you don't really, inflationary epoch makes it obvious, but you don't even need an inflationary epoch. If you go far enough out in the universe, the speed of galaxies just increases, and eventually goes faster than light, but it doesn't go past you faster than light, so it's allowed in general relativity. Dark energy also causes the distant universe to accelerate in its expansion. That's true, but it's not necessary to create distant galaxies moving away from us faster than light. Okay, so are there any galaxies in the observable universe currently moving away from us faster than light? So this is the observable universe. So the possible answers are yes, oh, lots of them. B, no, or by definition, they would not be in the observable universe. Or C, yes, but none that you can point to because light from them has not yet reached us. These are pretty tricky. This is level 3 stuff. And I wouldn't get these, so I'd had to ponder these for a long time. But yes, they're in the book and explained in a lot more detail in the book than I can do here due to time limitations. But I just love thinking about this stuff. Okay, people guessing? And the answer is, this is a bit tricky because the word currently refers to right now. So the best answer is A. There are lots of galaxies that you can see, but you're not seeing them as they are right now. You're seeing them as they were billions of years in the past. So if you go to where they are right now, they're further away, and they're moving away faster, and some of them are moving away faster than light. So it's a bit tricky, but yes, some of the galaxies, you look out, distant galaxies, it's seen by the Webb Space Telescope or even the distant ones from the Hubble Space Telescope. Yeah, the most distant ones, we see them, but right now, they're still doing their thing. We don't know what it is because we haven't seen them. We don't know what's happening now. We knew what was happening billions of years ago. They're moving away from us. So, and this is one of the final ones. You see a galaxy. There it is. You shine your laser pointer. Let's get this laser pointer back in there. You shine it toward the galaxy. Will your laser light from your laser pointer ever reach that galaxy that you're looking at? So you have your telescope, you look at a distant galaxy. Okay, I'm going to communicate with that galaxy. I'm going to shine a laser pointer at it. Yeah, so it might be moving laterally. Let's not assume it's not moving laterally. So if you can see the galaxy, A is, then you know there's a light path to it. So the answer is yes. B, no, the expansion of the universe is just too great. And C is it depends on the distance to the galaxy. And people are seeing it up. And yes, people are right. Best answer is C. Galaxies past redshift of about 2 will be moving superluminally soon enough so that your laser light will never, ever reach them. So if you wanted to signal, you say, oh no, I see something going on in the galaxy. I want to tell those galaxy aliens what's going on. There could be trouble. Don't develop that weapon or something like that. I'm going to shine my laser at them and tell them that through Morse code or something. Don't bother. Your light's not going to get there. Assuming the universe that we think of the concordance model of the universe that we think is going on. There could be bizarre things that happen in the universe. There, phantom energies or something like that could cause strange futures of the universe. But if it's going like it is now, without any great surprises, then your laser light will never reach that galaxy. And so some of the galaxies in the night sky, out of contact. And as the universe expands, that ability to communicate with galaxies becomes closer and closer. And so in redshift 2, in a couple billion years, it'll be redshift 1, redshift zero point 0.5, and we're falling out of touch with galaxies of the distant universe more and more as the universe expands. That's the strange world of Friedman, Robertson, Walker cosmology as solutions to general relativity. Okay, not my favorite question. We're running out of time, so I'll skip this one and just go right to, okay, sunrise and sunset. Well, I'm going to skip this one too. I'm just going to go, I think we're running low on time and I want some questions. So let's just go right to, we can review these. You can see these later. But I want to thank everybody. So here's a bunch of superluminal publications with some of my students, which has been, again, a hobby, a passion of mine, along with astrophotography for many years. So you can look up some of these publications. And the happy thing is you can own a digital copy of this book. I'll put it in front of me again so you can see it just by emailing me. And here's some reviews of the book. It's doing okay on Amazon. You can order it through Amazon, but if you just send me an email, I can send you a digital copy. The other thing I have to say is thanks again to the Memphis Astronomical Society. I hope this was entertaining for you about things that can go faster in light. And if you're just joining, just checking in, you can really do well by joining your local astronomical society, which in this case is the Memphis, because they have star parties. You can learn to look at telescopes. You can look at the universe. And if you have a big enough telescope, you can even see galaxies that are moving so far away, you can never communicate with them. So I want to say thank you to everybody for inviting me for this talk, and I'm happy to take questions even about the astronomy picture of the day now. And I'll stop sharing. So
Thank you, Dr. Nemiroff. That was incredibly interesting, and you actually asked questions I did not know the answer to. And you're gonna make me think about this more than I had originally intended.
Okay, I'm going to put my email address in the chat here. Let's hope I don't misspell it. There's going to be some strangeness. I just did. Now I corrected it. Okay. That is my email address. It's my last name that has to be spelled correctly, or you'll get a different book. And
By the way, Amazon only had 4 copies of your book left. Well, no, they only have 3.
Mm-hmm. 3 digital copies. But so again, I've been running with my colleague, been running APOD for 30 years. Seen a lot of astro photos. Will the closing of Goddard impact your studies? Okay. So I'm unaware that Goddard Space Flight Center will be closed. I understand it's being pared down quite a bit. And there's discussions currently of the library closing. But I don't want to get into the details of saying things about that. I don't know details. I don't want to present NASA policy. I'm a fan of Goddard Space Flight Center, and my current understanding is that it will not be closing. I have colleagues working there now who currently are not planning to leave. It might close in the future, but right now, Goddard, my knowledge, is not scheduled to close. Thanks for the question.
So I have a question.
Oops.
This is Rick.
Yes. Okay. Yes. Well,
so
it's my chat.
So
there we go.
So when something falls into a black hole, right? You as you go to cross the event horizon from outside the black hole, that appears never to happen, right? That
Correct.
whatever it is, the time slows down to the point, and although on the local frame, they've gone into the black hole, and I suspect anything happening inside the black hole is happening at the speed of light or faster, going toward the center, singularity, whatever it actually
Yeah.
exists in the middle of a black hole. In the
Yeah.
expansion of the universe, those galaxies, well, and I'm not sure this is even a decent way of thinking about it, but the cosmic microwave background, for example, is that not actually farther than is that moving away from us faster than the speed of light? And is it just stuck on that horizon by the light that's getting to us now?
You're exactly right. So that's actually very good insight on you. What happens is when things go over the horizon, when a galaxy goes over or the microwave background goes over, it doesn't disappear to zero. It becomes more and more redshift and it freezes. Just like if you drop something into a black hole, you don't see it disappear, you see it freeze at the horizon. And you see things freeze at the horizon of the universe, and that's what the microwave background is doing. So if we
Yeah,
wanted to communicate with the microwave background and say, hey, little spot, you're cool. I just want to say that. You can try, but it's not going to get there.
right, right. Cool. I got it right.
Okay, any work on Cloud 9?
Anyone else have questions?
I'm not familiar with the Cloud 9 project, Starless Gas Cloud. I might have seen a press release maybe today on it, but I didn't really study it, so I'm sorry I'm not prepared for that one. Well, why tachyons? So people do work on tachyons, but not me. Um, well, because people say what special relativity prohibits is from anything with mass from going from below the speed of light to above the speed of light, because then you need infinite energy. So people say, well, we don't know how it happens, but let's just say that something happened to be on the fast side of the speed of light. Then it doesn't have to cross over, so it's not forbidden, and it's true. But there's all kinds of energetic things that go on with cosmic rays and particle colliders. And so far, we've had several scares, but we've never had anything that's ever been recorded to go anything with mass faster than the speed of light. So all the energetic stuff we've seen, nothing's ever beaten it. So even though it's a possibility that there could be things trapped on the other side, there's no data to indicate that. And we know that we ourselves can't go there because we're already trapped on the slow side of the speed of light.
Don't tachyons are supposed to have negative energy? Is that
Yeah,
what
yes.
features?
Yeah,
Yeah.
you get into some really strange stuff with negative energy. Yeah. I don't study quantum tunneling. So quantum tunneling, which is actually discussed a little bit in the book, um, is there are some people who think that quantum tunneling can occur faster than the speed of light. But again, that has never been demonstrated. No signal has ever been transferred by tunneling faster than the speed of light. So it is not yet, and there are people, including me, who are skeptical that it will ever be. There's some tricky bit in there in the uh, quantum tunneling analysis that we don't fully understand. So I do not, even though I don't study it, I'm skeptical that quantum tunneling will ever be your telephone to faster than light phenomena. It's running up against too hard a law with special relativity.
Well, that's like the collapse of the wave function. Technically that happens faster than the speed of light, which is
Yes,
why
and
so many people have
that's
such
true.
difficulty with it.
That's also discussed in my book. But that does not communicate
Mhm.
information faster than light either. Yeah, you can't communicate with that. Yes, sure.
All right.
All right.
Well, being an astrophotographer, I have to ask,
Yes.
do you have any clue how many astrophotography photos you've seen since
How many I've seen?
Yeah, you should have one of your students work that up for you.
365 times how many days?
Yeah, so we
No,
get
but he's
about
going
20.
through probably 50 per day.
Oh,
We get
yeah.
about 20. We get about 20 a day, sometimes 25,
Hmm.
20 a day for 30 years.
Okay.
So you can work that out. So I don't know if Zoom has a little calculator built in, but I have a calculator on my phone. So let me see if I can do that.
I got it.
Uh, so let's see, it's
365 times 30.
365
times
days times
0.5,
25 a day, let's say, times 30 years.
273,750.
Yeah, it's 200, about 270,000 photos.
And you remember them all, don't you?
Everyone. But that
Okay.
no, but what's great is I can tell you though big trends and that astrophotography is just getting so amazing. That way
Mhm.
back 20, 30 years ago, we were not seeing the quality of astrophotography because the CCDs are better, the CMOSs are better, the image
Processing.
processing is better. Just you know, there's so much that is advanced in amateur astrophotography that the images are just amazing. And people have not only that, people have more time to spend. The digital things you can look on YouTube and get tutorials on YouTube. You can go to conferences and get tutorials that tell you how to process your images and bring out things that weren't seen before. So a lot of the amateurs are picking out little faint things that sometimes are very scientifically interesting that the professionals can't do it because professionals look at really small parts of the sky very deeply. But amateurs can look at wide swaths of the sky and they can just keep imaging exposure after exposure, exposure, night after night after night, and building up stuff that people haven't seen. And we didn't see that 30 years ago, 20 years ago. Only David Malin, if you know who he is, because he had the Angle Observer, the AAT in Australia. So he could do it a little bit, but he was just one guy. So we were just constantly amazed at what people are able to do. So, and it just keeps getting better.
Yeah,
With AI, it might even get better yet. We don't know what the boundary is on that. We have to be careful though, because it could get faker too.
that's right.
Yeah. Well, all right. Well, thank you so much for speaking with us this evening. And uh, I've got a copy of your book coming. What I'd like to do is send it to you and get you to sign it and send it back. I'll talk to you about that.
Okay, sure.
And uh, this has been excellent. We'll have this uh, posted on our YouTube channel in the not too distant future. As soon as Steve gets a minute to take care of that. And
Mhm.
absolutely wonderful. We've got, by the way, I saw our attendance was up around 40 something people, which is high for us. So you were quite the draw tonight. So thank you very much for sharing this information with us and being willing to come on here and talk to us.
It's been my pleasure. Thanks to everybody.
Thank y'all. Thank you, everyone. And remember, we need some telescopes for Saturday the 10th, I think it is, for Pinecrest. So if you're inclined to volunteer for a public observing session, get in touch with me, Rick at memphisastro.org. Thank y'all very much and have a good evening. And until next month, clear skies.
Bye now.